Hello everyone. I would like to start with a quick review. And we started rotational motion last time, and I think it's important to review the material because there are new symbols and we just need to get used to them. So we start with the position, and I'm going to show the mapping as well from linear to angular or rotational. So in terms of linear, I'm gonna think in terms of also like 1D. Okay, so instead of thinking about the three-dimensional position vector r, I'm gonna say if it's one dimension and it's along the x direction, then we show position vector using x, right? And in linear form, position is x, but in angular form, it is theta. Okay, and in linear form, it is meters. In angular form, it is radians. Okay, so these are the units. And for the velocity, we had v as the linear velocity, or sometimes we also call it tangential velocity. And that is related to omega. And again, linear velocity velocity unit is meters per second, and in angular velocity, which is omega, is radians per second. Okay, and the acceleration was the third motion descriptor, and we used a for the linear motion, and we have alpha in the angular motion, angular acceleration. Okay, so a was meters per second squared, and alpha is radians per second squared. Okay, so it's very related. It kind of, if you realize that meters is radians in the angular form, and you can replace the rest of it. And be careful with the radians, because if it's usually not given in radians. It may not be given in radians. If it's degrees or given in revolution, then you have to convert it to radians. So let's just think about the conversion factor for that. So we have 2 pi radians, right? You don't need to write radians, but I'm just going to emphasize it. It's 360 degrees, and that is 1 revolution. Okay. So that was the conversion factor, and you're gonna use it a lot. So it's you don't need to memorize it, but it will be very easy to do so because we use it a lot. So these are the this is the mapping. Okay, so far, and we will add more to this list, but this is what we have so far. Again, you're using Greek letters theta, omega, and alpha so far. We will add more, so make sure to get used to them when we are doing it, so that you don't have too many of them to kind of learn later on. Okay, so next thing is let's think about the equations as well. Okay, so for the position, again, was x, and theta is what we are using for angular. Let's start from the displacement. In one-dimensional case, we said delta x is our displacement, and that's x2 minus x1. In angular form, we have delta theta, and that's going to be theta 2 minus theta 1, right? Very similar, just replace x with theta. And now if we define the angular velocity, but we looked at the velocity in 2 different forms, right? It was average velocity and angular and instantaneous velocity. So we show the average velocity as v bar, and that was delta x over delta t. So I'm writing these in 1D case, so it's in chapter 2. So I'm kind of ignoring the vectors, but I really hope that we're already comfortable with the vectors. But here v and x are vectors, right? I'm just dropping the vector signs, but they are vectors. Just remind yourself about that. Similarly, so I'm gonna say v goes to omega, x goes to theta, Here you go. We have the average velocity, angular velocity now. Okay, and we can write the instantaneous velocity. And if you remember, we take the limit, right? We need to, this average is in terms of time interval. Now we need to make this time go to 0. Delta t goes to 0, so we need to take the limit, and that becomes simply v. We drop the bar because bar is average, and that's going to give us the derivative, dx over dt. Same thing for omega, it's going to be d theta over dt. And we also did a similar thing for, so these two are velocity, right? Average and instantaneous. Now we did the same thing for the acceleration. We did average acceleration and then instantaneous acceleration. Average acceleration is change in velocity over time. And that is now a goes to alpha bar, and v goes to omega, delta omega, and over delta t. Okay, so again, nothing really different since we've used the linear form a lot. You don't need to memorize it. The equations are given in the equation sheet, but I think it's very straightforward once you see the relation. Now the instantaneous one is again the derivative of v with respect to t, and same thing for alpha. It is d omega over dt. Okay, and again these are the acceleration, average and instantaneous. Okay, so these are what we've seen so far. And later on then we said that this is for a specific case when acceleration is constant. So we have constant acceleration, and it could be linear or angular, right? So I'm going to say A or alpha. Then we had two equations. That was our step 1, right? We had 3-step process. Step 1 was writing those equations. So I'm going to write it in one dimension again for x only. X equals to x0 plus v0 t plus 1/2 at squared. I'm assuming, again, my motion in only one dimension, so I'm dropping some of the components. Like this should be, for example, v0x, this should be ax, but if it is only axis, it's one dimension, this is okay. And again, I'm going to drop this x as well. V is going to be v0 plus at, assuming this motion is only along the x direction. Okay, so we have the same thing. So x goes to theta, theta equals to theta 0, v goes to omega, omega 0 t plus a goes to alpha. Oops. Let's go down. And then v goes to omega, v0 goes to omega 0, a goes to alpha, and that's your equation. Okay, so this is what we covered so far. We're just relating things, and we're gonna add more to that soon.